Sorry, I had to drink my coffee.
Yeah, it's important.
I mean, it's required in Seattle to make sure to have the coffee ready in the morning. Well, good morning, everyone. I'm going to talk, I think, for about 20 minutes about LSST. I'm going to split my talk. I'll spend the first little bit just reminding people or sharing with people what LSST is, what kind of data it produces, and I think hopefully that will spark ideas about what are the sorts of technical signals we'd be searching for. And then I'll spend the second part of the talk um, trying to outline what I think are some of the ideas for types of signals that I have been thinking about, that I've been working with people on developing, or ones that have just come to me in the wee hours as I've been thinking about how to do this. So I will give my conclusion, which is if you have more ideas about signals that seem plausible with LSST or these kinds of surveys, reach out. Let me know. I'm trying to collect kind of a list of these as I make this talk and give it over and over. So I would love to hear feedback and thoughts from people. Okay, so hit the play button here. Can everybody see that slide?
Looks good.
Excellent. Okay, thank you. All right, so optical SETI with LSST. Okay, so first, just a ground level. Where are we with LSST? What is the current status of the observatory and the mission? I'll tell you more about what it is here. So this is actual footage from a couple months ago from Chile of the Vera Rubin Observatory. Big steps have been taken this year during the pandemic. There is a dome now. There is a major building, and they got the largest crane in Chile up on the mountain, the largest mobile crane, up to put on the top end. So that's a 3 meter-ish secondary mirror sitting above an 8.4 meter primary, which is also sitting in its cell down there, or maybe it's actually in storage during the shot. But the point is the telescope is largely constructed, and this is really, really exciting. The pandemic has pushed construction of the facility back by about a year for first light. So instead of the end of this year, it'll probably be mid next year for official first light. And then we'll see commissioning data out of the observatory. Let's see, move this window so I can actually see my slides. Look out, Zoom, get out of the way. Okay, so what's under construction there in that video, in that drone shot, is the Vera Rubin Observatory. That is the name of the entire building, the entire facility, and the entire project. It is the Vera C. Rubin Observatory. The actual telescope inside that we saw being constructed is the Simonier Survey Telescope, thanks to major donations from the Simonier Foundation. And the project that the Vera Rubin Observatory, with the Simonier Survey Telescope inside, will conduct the first project, a 10-year mission, will be the Legacy Survey of Space and Time. It used to be called the Large Synoptic Survey Telescope. That was the name of the whole facility, but then we named it after someone. So the Legacy Survey Space and Time preserves our acronyms. So we don't have to change all of our code. And I think it captures what the point of the telescope really is, which is to create not just a survey of space and over a 10-year time span, but create a legacy survey, something that will lay the foundation for hopefully another generation after this observatory. And then as was mentioned just at the beginning of the talk, Berkeley and the Breakthrough Group have joined the LSST Corporation, which is a nonprofit entity that sort of wraps itself around these three pieces of the project. It is not responsible for building any of it, but it is responsible for guiding the science output of the facility. So trying to maximize the science we produce. So they help facilitate science collaborations, workshops, grants, postdoc programs, things like that. So I'm really excited to be able to collaborate with people via the corporation. Okay, so the Legacy Survey of Space and Time is a large, deep optical time domain survey at its core. It has other science goals besides technosignature work, things like studying the edge of the universe, looking for variable objects. It's a 6-band photometric survey. You can see down the bottom right the 6 band passes, and including, I think most interestingly, a Y band out there around 1 micron, which is kind of cool. It's much redder than was previously done in things like the Sloan Digital Sky Survey. It's a 10-year baseline, and you get something like 1,000 epochs per object over all the filters over 10 years, something like that. That's like the rough number when you spread everything out. That means that we're surveying something like 17 billion stars within the Milky Way. There's objects outside the Milky Way, but I study stars, so that's what matters. There's other things out in the night sky, but 17 billion stars. That's 20 terabytes of imaging a night. That's a lot of imaging. I wouldn't want to put that on my laptop, but that doesn't seem like a terrifying number anymore. We have cloud computing facilities that I think this is going to be totally processable, no problem. And each visit is a pair of 15-second exposures. It's a 30, so not nominally a 30-second visit per image with a 24th magnitude visiting depth in the optical. That's split into two 15-second exposures for cosmic ray rejection and things like that. And the survey will conduct a lot of automated processing in real time. So it will generate real-time point source, galaxy, and moving object detection and cataloging, and all these things will be available essentially worldwide in almost real time. So it's a really exciting survey. You can see, since it's located in Chile, you can see the sort of coverage map there on the top. We're surveying almost the entire southern sky and a little bit in the northern sky, and some little pieces of the galaxy and stuff that are gonna pop up on. So that's the first and the primary data type that comes out of LSST. It is a big survey, and so anything you can do with wide filters and fairly sparse long exposures, that LSST is great for. That is the first data type. The second data type, which is interesting, is the real-time alerts. So LSST has promised to deliver, within 60 seconds of each image being taken, they will conduct difference imaging from a reference catalog, look for, I think it's 5 sigma outliers. I think that's the threshold these days. And they expect, and so either positive or negative outliers from that reference catalog will be alerted and posted online within 60 seconds of the shutter closing. These are massive images, so this is actually kind of an amazing computational feat right now. It's actually really challenging to do this kind of reference and difference photometry that quick. But they're expecting around 10 million, maybe a little bit more, of these real-time alerts published each night. Many of these are just junk. They're just variable stars that are oscillating up and down. And then as the survey goes over and over in time and visits these fields over and over, they'll be able to flag those and ignore them. There are these so-called brokers which host these filters. These are just endpoints that people like you and I can go to find these alerts. People are developing various apps and interfaces and things where you could trigger other observations or set up filters to look for your favorite kinds of alert, or if your favorite star does something wacky, hint, that's what I'm thinking about, then you could set up a trigger to alert you that this one of these alerts has been signaled. And what's interesting is the Zwicky Transient Facility, ZTF, already is running out of California and using many of the same broker technology that we're developing here at the University of Washington for the Rubin project. And they're already publishing between 100,000 and 1 million alerts a night. So if you're interested in this kind of real-time alert transient science, there's a way to get involved right now. Okay, so those are the two primary types of data that LSST conducts. There's no spectroscopy, it's just imaging. It's fairly deep imaging, so follow-up spectroscopy is actually a bit challenging. But there is the possibility of real-time monitoring to a depth that has never been done before in the night sky. I guess one thing I didn't mention is in the main survey, maybe it's written here, but we survey the entire night sky roughly every 3 nights. So you get about, because of the width, the size of the facility, you get about a third of the sky each night through coverage. So your favorite star will get observed 2 to 3 times a week, something like that. So it's fairly sparse data when you're thinking in comparison to like TESS. Okay, so here's a nice parameter space that Shelley Wright put in a white paper last year. And this paper argues, and I agree, for the now traditional optical SETI work, which is mostly at the high time resolution end, so laser pulses and the like. We've seen lots of great stuff on this already in this workshop. So that's everything on the left side of the diagram, and LSST is just not in that space. LSST is everything on the right side of this diagram with 15-second exposures and up to 10 years. So it goes a little bit to the right of this box. Possibly the facility is going to run longer than 10 years. So we're going to see there's a huge dynamic range. We can see lots of small scale stellar variability, lots of simulations of flares and star spots and little eclipsing things that we're going to be able to detect. And then of course we'll get novae and things like that. Great stuff, big luminous events. But I would argue that there is a lot of work to be done on the right end of this diagram still, piggybacking on the things that nature is producing in abundance, like novae and like flares and like things that stars normally go bump in the night and do. So I think there's a lot of opportunities here. But it is interesting that there is just sort of no overlap with the laser SETI as far as I can conceive, and I haven't heard any arguments otherwise. So that poses this is the big question. We have a big survey with lots of types of data, big computational abilities and resources at our fingertips, but we have these sort of wide optical bands, these very long exposures as compared to traditional optical SETI, with a slow and sparse cadence. So this kind of, it's a huge resource, but it sort of breaks our expectations of what we would think about designing an optical SETI mission for. So what are the phenomena or the signals that we might use to do optical SETI with? And so this is the second half of my talk, is let's just talk through some of the ideas, and you can shoot them down and tell me they're a fool's errand, and that's fine. I would love to hear that, because then I can delete this slide from my slide deck and never give it again, and I can come up with a new idea. And that's how I think we should proceed. We should develop these ideas together as a community. On the right here, just to remind us, there's a great diagram that came out of a Technosignatures workshop, I guess a couple years ago now, which just reminds us about what are the best signals, or the most, information rich, the detectable, the long-lived, and I think it's the top portion of this diagram, if you can see it, that the searches can be done now. They're fairly cheap because we have computer hardware already to look for supernova and other things with LSST. And there are ancillary benefits. We can detect these things, and the outliers or the false positives will be fascinating nature papers that we'll write. So I think there's a lot of benefits to doing this search, even if we're not, even if it's not necessarily the optimal search as we conceive it. I think there's a few types of signals we might look for. There's, of course, variable profiles and time, so things that have interesting brightness changes. There's 6 optical filters, and one in the near infrared. So things that are in strange places in the sort of spectral energy distribution, or that move into strange places in the spectral energy distribution over time. This is a very deep and wide survey covering a large area of the sky and a large volume in our galaxy, if we think about the stars that it's mapping. And so spatial and temporal coordination of things that change both in space and time with some sort of meaning. And also similarly, the spatial distribution of things, finding things in certain places or moving in certain places. I think these are the broad categories of signals that we might think about. Okay, so let's run through some example ideas for a few minutes here. The first, and I think the best the best characterized, is Vasco, which we've heard about and is just great. So I don't really need to cover Vasco a lot because it's awesome and we've heard about it. So here's a great example on the right of an object that possibly was there and then doesn't appear to be there anymore. Now, LSST can play in this space in 2 ways. We can look for more candidates, just like here in red, and because it's a very deep survey, we can go check on all these old candidates that have been developed from like legacy photographic plates. So lots of possibilities with Vasco. It's just a matter of writing database queries to go look for these kinds of candidates and follow up. I think this is a great first step. When we're thinking about Vasco, we're talking about presumably Dyson spheres or other kinds of technology like this that are being constructed. So I think there's a few ways to look for Dyson spheres. I'm certainly not a Dyson sphere expert, but that is one possible type of signal or type of system we might look for. And particularly thinking about utilizing the reddest band passes or color outliers. Again, as I said, there's an interesting spectral energy distribution component here that we might look at. So I think broadly speaking, these are places we might look. And we've heard about this as well already, the so-called Boyajian star, or the very strange variability profiles that are perhaps unexplainable. I mean, it might just be rocks and dust like everything else, but it's unexpected and unexplainable. This is a good example of our byproducts being nature papers that will fascinate and excite the community. So this is Boyajian star as detected by Kepler. Very strange variability, both up to 20% flux dips, and then lots of equally bizarre 1 to 2% variations, including long-term dimming that seems to come and go over 3 to 4 years. See there on the bottom panel. So again, I'm not necessarily the expert on this object, but you can talk about the machine learning that Anne-Marie and Dan were discussing yesterday about how to find these kinds of strange variables in our data, and LSST will certainly be a great hunting ground for these kinds of machine learning approaches to look for these weirdos. And just as a small advertisement, we've started a preliminary project like this with ZTF here at UW. And there are lots of really cool things that go dip. On the right are some objects with some strange asymmetric dips. They are probably, many of them are probably cometary kinds of things, or things with disks. On the left, some of the things that look more like long eclipses, very long duration eclipses. So there's lots of really great astrophysics to do when you look for big, strange dips. And so that is a project that I think will be very fruitful with LSST as well. Okay, there are interesting types of sort of signal modulations. I really like this paper on the left about laser cloaking, the sort of cartoon diagram here, how to hide your eclipse if you had a big laser. Looking for something that is a normal clock, like an eclipse or a transiting system where the eclipse goes missing one day and maybe comes back, something like that. Looking for a clock that somebody has messed with, I think, is a good example that LSST will be well poised to do. And then on the right, I think LSST is not the optimal instrument for this kind of work of looking for strange transit shapes, just because the difference between a triangle and a circle is very small. But there is the possibility, again, of sort of looking for strange transiting profiles. And LSST will certainly have a great number of transiting things or eclipsing things. So I think looking for things that don't fit our transit expectations or our eclipse expectations are a good place to look for. And then in the sense of signal modulation and weird signals, there is unusual patterns in our data. So here is a project that I started kicking around a couple years ago about trying to recover repeating but non-periodic signals in our data. And I see a message in the chat. Oh yeah. And so yeah, so here's an example of if somebody, instead of using a periodic signal, which all of our technology is tuned to right now, that instead you use a Fibonacci spacing instead of a periodic spacing. Can you use the same sort of dispersion minimization technology? And of course, if you know the pattern, you can. And so I think there's a lot of games to be played here of looking for different kinds of signals. This is both applicable to LST and also things like TESS. There is, as I said, the coordination in space and time, or other dimensions like eclipse period or something like that. If you had some system that you were trying to use as home, and lots of beacons around trying to point back, like lighthouses, back towards home, you could imagine there being spatial correlations between a property like eclipse times or outburst times, the coordination both in space and time. I think this is a really underdeveloped and really interesting place. And the best idea that I know in this sort of space and time phase space, which I'm excited about, is the so-called SETI ellipsoid. And so if you don't know the SETI ellipsoid, there's a great paper in 1994 that describes the technique with respect to supernova 1987A, using that as kind of a signaling event that everybody in our galaxy would presumably see, a rare event that we would take notice of that isn't something that happens every day. And so the idea being that if here we are as the observer on Earth, and over there on the left is the supernova, then if there is a possible star with a civilization that wants to get our attention based on that so-called Schelling point, or that signal, that there is an ellipsoid, a three-dimensional ellipse, that is carved out by the propagation at the speed of light of that supernova, reaching that that civilization, and then if they were to then beam out we saw it, or rebroadcast the thing, or send out some kind of nova of their own, I don't know what the signal would be, but the time it would take that signal to reach us defines an ellipsoid, which is growing with time. And so as the supernova's light curve itself reaches other civilizations, and they have the opportunity to then transmit out into the galaxy saying that we've seen it, we can search that ellipsoid, and it's well defined in space and time. So this was an example that was proposed actually a long time ago. This is a great paper from the 90s that describes it from 1987A. And 1987A seems like it was quite a long time ago in the sort of human time scale, but it really wasn't. Of course, right? It was only like 40, no, not even 40 years ago, right? So So here is the Gaia 100 parsec sample, and there's edges of things right on the edge of the 100 parsecs there. The stars in red, so we're in the middle here. The stars in red have not seen supernova 1987A yet because they are more than 40 light years behind us in that light propagation timescale. So just in the 100 parsec sample, almost half of the stars haven't even seen 1987A yet. And here we are right in the middle, and all the stars in pink or purple are the ones that could have seen 1987A and then rebroadcast something back. So they are they're inside the SETI ellipsoid. And that is a small fraction of stars. And you can see that that ellipsoid points towards the LMC, points towards 1987A. I think this is a really great technique because it gives us a place and a time to look and to pay attention to. And so if you think about the possible signals you would want to look at, which stars do we care about in this ellipsoid? It's the ones on the sort of the surface, the three-dimensional surface of the ellipsoid. And so there are a few dozen of these when I did this calculation recently that are so quote unquote on the ellipsoid, that are on that surface within a tenth of a light year was the threshold that I gave. You can think about how errors and uncertainties in distances and uncertainties in event times propagate into big uncertainty envelopes in which stars should be on the ellipsoid. But even then, this is not that many systems when we're talking about 17 billion stars to monitor. Having some sense of which stars we would care about as that information propagates, I think is really cool. So that's just one signaling event. That's just supernova 1987A. It's sort of the best and our favorite. But I talked about this idea, or talked about SETI with LSST a few years ago when I visited Berkeley. And Jill Tarter, I wanted to say thank you because she suggested I also consider things like galactic novae, something that is also bright and fairly rare, but a bit more abundant. They occur every few years instead of once a century or two. So that gives us an order of magnitude or so, or maybe more, of these objects to look around the sky. So here's a couple hundred of the best characterized novae, just shy of 300, 278 it looks like. And you can see they go back. There's a few within the last couple of years in log time here on the bottom. And there's some of these novae we know that go back 100 years, which is really fascinating. And so you can do this same SETI ellipsoid calculation and figure out that even with really tight tolerances for which objects and error uncertainties and timing uncertainties, there are thousands of stars every year in our neighborhood that would be good candidates for looking for SETI ellipsoid signals. So being mindful of which stars we look at, when you see some interesting flare, interesting event from a star, maybe saying, hey, that could be something that's on the ellipsoid. Let's do some more follow-up of that object. Okay, and finally, it's been in the news a lot in the last few months. I don't want to talk about this object specifically, but the idea of looking for unnatural moving objects within our solar system. So a huge data product, a fascinating and delightful and important data product from LSST and the Vera Rubin Observatory is asteroid and comet hunting. Within the first month that LSST goes online, they will find more asteroids than have been found by all missions in all time. And so there's a lot of people at the Minor Planet Center working hard to add an extra digit or two to the naming convention because they're going to fill up all the catalogs really quickly. But because the imaging is sparse in time, they are doing a lot of work to project and do real-time orbital fitting of where objects should be, so that when they see another little streaky thing on the camera, they can associate it back to something they had cataloged days or weeks earlier, and then get a better handle on its orbit. So trying to do this real-time orbital monitoring and propagation is a really cool computational challenge underway right now. And it provides us yet another axis to look for something that is very, very nearby, something that is coming through our system that is possibly unnatural. If things take, a 90-degree turn in the sky, that would be a big signal that something is afoot. And so I think Oumuamua was a great and interesting event. LSST should discover several of these per year. We expect possibly several per month, depending on the incidence of these things. And I think it's a really interesting opportunity. So I know this is another place that we shouldn't discount. Okay, and that's the catalog of ideas that I have. And let me just review really quickly. LSST is one of many awesome facilities in this sort of new era of optical astronomy and optical SETI. It's not like our traditional optical SETI, if there is a tradition of doing things at short time scales, but instead we have a capability of doing automated monitoring to a depth that has never been achieved. I think LSST is an instrument and a facility and a project that is really harmonious with things like TESS, and on the brighter end, things like Assassin and EveryScope and a lot of other facilities. And what I would love is for us to develop these kinds of technologies, these kinds of ideas for signals, and that means let's develop code that can search these databases, because if we can do it with LSST, we can go back to the archives from Sloan Digital Sky Survey and others, and we can go forward into the archives of things like Assassin and EveryScope, and hopefully what we'll develop is extensible portable code to do these kinds of problems. And that's all I got.
Fantastic. Thanks, Jim. That's a lot of ideas. The next 6 months we'll spend going over those. Are there any quick questions for Jim? And these things are going to come up in discussion later too. So I would say, you know, you can let that mull in the back of your brain, but if there are any kind of questions up front, do you have time? I think people are just too busy mulling over all of the ideas.
Mulling over the coffee. I'm mulling over the fact that this coffee cup is empty. And I'm gonna have to go refill it.
Yeah. Okay. Well, thanks again, Jim. I said, well, oh, there's Shelley. I think actually it's a great one too. Now, in that phase space chart you showed, you had LSST covering basically this half, and something like PanOSETI covering the other half of that phase space.